Now I wanted to look at a specific resonant example to tease out a few more important points. So let's say we have the following circuit. I'm going to write it small so we have lots of room. We have an AC voltage source that is connected to an inductor, a capacitor, and a resistor all in series. This is a 5-volt source, and we are going to change the frequency of it, so I'm not going to write a frequency yet. This is a 1 Henry inductor, a 1 microfarad capacitor, and a 20 ohm resistor. So to start with, we can find what our resonant frequency is. So omega naught we know is equal to 1 over the square root of LC. So I already had the square root. So square root of 1 over LC. So plugging these values in, I have 1 over 1 times 10 to the minus 6th in the square root. So this is going to give me a 10 to the minus 3 on the bottom. So that's going to give me a 10 to the 3 in the numerator. So that's a 1,000 radians per second. So remember, F is omega over 2 pi, which in this case is going to be about equal to 159 hertz. So 1,000 radians per second is about 159 hertz. We don't need this frequency value. I just, am describing it in terms of units that we're maybe more comfortable with. We're going to use the radians per second though, because it makes the math a lot easier. Fewer pi's floating around. So I'm going to write that up here. Omega naught equals 1,000 radians per second. Okay, so let's calculate the response of this circuit to different frequencies. So let's make a table here. So let's look at omega equals 10 radians per second. That's like roughly 1 hertz. Omega equals 1,000 radians per second, which like we said is roughly 159. And then omega equals 100,000, which is 100 times higher than 159. So that's, tens of thousands of hertz, 15,000 hertz or something like that. Okay, so for those different angular frequencies, and of course this one is the resonant frequency, but we want to look at one below the resonant frequency and one above the resonant frequency to get a feel for what's going on, I think. So let's calculate our reactances first. So we have the reactance of the inductor and the reactance of the capacitor. Okay, so reactance of the inductor, remember, is omega times L. So 10 times 1 is just 10. 1,000 times 1 is 1,000. And I'm just going to write 10 to the 5th ohms there to save some room. For XC, we have, we'll just do this really quick. So this is 1 over omega C. So C is 10 to the minus 6th. So 10 times 10 to the minus 6th, 10 times 10 to the minus 6 in the denominator is going to give us 10 to the minus 5 in the denominator, which is going to give us 10 to the 5th ohms here. Here, 1 over 1,000 times 10 to the minus 6 is going to be 10 to the minus 3 in the denominator, so this is 1,000 ohms. Of course, we already knew that because these two have to be equal at the resonant frequency, so that's a good check on our work, I guess. And here, when omega equals 100,000, we have 1 over 100,000 times 10 to the minus 6, which is going to be 1/10 in the denominator, 0.1 in the denominator, so that's going to give us an impedance, a reactance of 10 ohms. So this is kind of symmetric. Not all problems work out this symmetrically. I just happen to have chosen nicely spaced numbers for this example. Okay, so let's remember that for all three of these cases, of course, our resistance is not changing. It is 20 ohms each time, right? And I'm going to erase these, but just so we can kind of visualize this, I want to draw our impedance on the complex plane for each of these three. So, for example, here I have a inductive reactance of 10 ohms. So that's 10 ohms up. This worked a second ago. 10 ohms up, 20 ohms in the resistance direction, and then 10 to the 5th ohms in the negative direction. So this goes, way down through the floor or something. So this total impedance that we get if I draw this more to scale, it is like something like that. That is the total impedance we get. Here, we have 1,000 and 1,000 that cancel out exactly. We have 1,000 up in the plus J, 1,000 down in the minus J, and then 20 ohms. So the sum of those three is a very small 20 ohm vector in the real directions. This is just a vector pointing to the right. And then for 100,000, we have our inductive reactance is the big one. And so similar to here, when we add these together, it's not much, and then this big thing gets added to it, so it's really big. Our total value of Z, I can erase these. If we want to figure out the total value of Z, right, this is like the magnitude of Z total. We'll just do one of these and then you'll see why we don't need to do all these. So in the real direction, we have 20 ohms. So this is like the square root of 20 squared plus the difference between these. So 10 to the fifth minus 10 quantity squared. So if you calculate this, if you type this into your calculator, this is very nearly equal to 10 to the fifth. So this capacitor is totally determining what's going on at this frequency. The inductor and the resistor are basically not doing anything. They almost might as well just be wires. It's like the capacitor is just there by itself. It so dominates this equation. So for this, we get 10 to the fifth ohms. For omega equals 100,000, the math here actually works exactly the same. We get the same 10 to the fifth ohms. Here it's not the capacitor doing that business though, it's the inductor. The inductor impedance is the part that is dominating. The capacitor and the resistor are the ones that might as well not be there. And here, these two are exactly canceling out, which leaves us just with a resistance of 20 ohms. So you can imagine on this graph of Z as a function of omega, I guess I should draw like this. I drew it like this before. This is a really, the change from the resonant frequency to the high part might be really big. This is a factor of 10,000 or something like that. Okay, I'll keep this column up. What the heck? Okay. So we did that. We could have put, if we wanted Z total, we could put, J's or minus J's on these, but the magnitude is good enough for us. If we know this magnitude, we can find the magnitude of the current. Also, because remember, Ohm's law is V equals IZ if these are all complex numbers, but since they're complex numbers, we can also just take the magnitude of each of these, and this equation is also true, which means the magnitude of I is just equal to magnitude of V over the magnitude of Z, which is just 5 over whatever this column is here. So 5 divided by 10 to the fifth is going to give us a current of 50 milliamps. Down here, we still have 5 volts and it still is 10 to the fifth, so this is also 50 milliamps. And here, in the middle, we have 5 volts divided by a much smaller number, 20 ohms. So that's actually going to be 0.25 amps, or if we want to put it in terms of milliamps, just as a comparison to its neighbors. Oh, sorry. Strike that. This is microamps. I don't know how far back I was saying it wrong. This is 50 microamps. This is 50 times 10 to the minus sixth, right? And this is also 50 microamps. And so if we put this 0.25 amps in terms of microamps, that is 250,000 microamps. So this gives you a sense of how big of a difference there is in how much current flows close to the resonant frequency and far away from the resonant frequency. I'm going to erase some of this to make room. Let's see. I guess I should keep Z total and I. Okay, we'll try to cram this in on the right. No, this isn't gonna work. Okay, so under each one of these, I'm gonna draw a little other part of the table. So down here, I'm gonna put the voltages associated with the inductor, the capacitor, and the resistor for each of these three cases. So remember, each of these components in series is going to have a voltage drop across it individually, and we can figure that out from the voltage divider equation or from Ohm's law. The voltage divider equation, remember, is going to be that impedance divided by the total impedance. So times our 5 volts. So let's do one of these in the open. So for 10 ohms out of our 10 to the 5th ohms, VL is going to be 10 over 10 to the 5th times our 5 volts. So this is going to be 5 times 10 to the minus 4 volts. So this is a very, very small voltage on the inductor. This is, we're going to say, approximately equal to 0, and the same for the resistor, which means the capacitor is approximately equal to 5 volts. This should not be surprising because, like we said before, the capacitor is the thing that is totally dominating the impedance of our circuit. So the capacitor is the thing stopping the current from flowing. It is the thing that has all of the voltage across it. It's like a really big resistor in series with everything else. Down here, we have a similar thing happening, but it's the inductor that's really big. So here, this voltage is about 5 volts, 4.99, whatever, and this one is about equal to 0, and this one is about equal to 0. All right, lastly, for our resonant frequency now, something funny is going to happen. And this I want to write down. I'm going to erase these to make room. So let's look at ZL over Z total at the resonant frequency. So ZL is 1,000, I guess, this is really J times 1,000. We might as well keep our units, or keep our complex variables. Z total is equal to 20 ohms, right? Because these two exactly cancel out. So here, 1,000 over 20 is going to give me 50. So this equals 50 times J. The J is just telling us the phase here. And if we multiply this, this is not the voltage divider equation, this is just the fraction part of it. If we actually multiply this by the 5 volts, so we have 5 volts times ZL over Z total. This is the voltage across the inductor at the resonant frequency. This is equal to 50 times 5 volts. This is 250 volts. How the heck is that possible? How can we get a bigger voltage across the inductor than we applied to the circuit in the first place? Is this correct? Indeed, it is correct. And it turns out this is exactly the same phenomenon as your little mass on spring. You can wiggle your hand up and down this much and get a much bigger size in the oscillating response of whatever thing is hanging from the spring, as long as you're really close to that resonant frequency. So the same thing is here. For a little wiggling at the input, we get a very large oscillation on our different components. So this is 250 volts for each of the inductor and the capacitor. Now, how do these still add up with Kirchhoff's law to give us a 0 around the loop? Well, these two, if we're looking at them in terms of complex numbers, these are 180 degrees out of phase with one another. So we're adding together a voltage that looks like this to a voltage that looks like this when they're in series, adding these delta V's. And so they're canceling out everywhere, and they don't add to the overall delta V around the loop at all. So that's how that works. The voltage across the resistor, of course, is 20 divided by 20, since the total Z is just 20. So this is just the same 5 volts that we are applying to the circuit. Okay, so this has been a fun tour of a resonant circuit, and I think we've seen some important things here. While we're working on this, we might as well calculate our other our other resonant variable values as well. So let's erase a little bit to make room for that. So for this resonator, remember we have some graph of current versus omega that looks kind of like this. And remember, this was the bandwidth, and we can calculate how big that bandwidth is now. And in terms of omega, in radians per second, the bandwidth is just equal to R over L. In terms of F, the bandwidth is equal to R over 2 pi L. So R over L here. So R is, of course, 20. L is our 1 Henry. So the bandwidth is 20, and the units of that are radians per second. Remember, the center was 1,000 radians per second. So that means this peak goes between 990 and 1,010. That gives us a total bandwidth between the two of 20 radians per second. We could do the same thing with our frequency f. The numbers aren't going to work out as nice, so we're going to skip that for the time being. We can also calculate the quality factor, so let's do that. The quality factor for this resonator, we can do it two ways. One way is we already know the bandwidth, which is 20, and we already know the resonant frequency is 1,000. So Q is equal to the resonant frequency over the bandwidth. So that's 1,000 over 20, which is equal to 50. So our Q is 50. Incidentally, this means on average, if we were to turn off our voltage supply and let it resonate on its own, it's going to oscillate 50 times before its amplitude decays by a factor of E, because you have this exponential decay. We won't need to know that, but just that's, if you can have some sense of what Q is. It's like how many times it will oscillate on its own before the oscillations die out. The other way of finding Q, of course, was XL over R, and this was XL at the resonant frequency. So that was 1,000 ohms divided by 20 ohms. So that also gives us 50. Remember, this was 1,000 radians per second divided by 20 radians per second. This is 1,000 ohms divided by 20 ohms. It is a coincidence that those are the same. In general, they are not the same values. All right, I think that's all of our different things we can calculate for this. Yeah, so resonance is fun and interesting.